Okay, hello, welcome. In this video, I'm going to talk about an asymptotic analysis of the growth rates of common algorithms. Okay, so I hope to cover these topics. Now, this is really just an introduction. I'm really going to go over kind of the main point. So, to me, I mean, this is an important topic. It can be really useful in the real world as long as you know kind of the basics of these things. But you don't really need to So, I mean, there's a whole area. This is really getting into some really theoretical computer science, right? But this has some very practical things too. So in terms of what we run into every day, though, is very useful. So there's lots of common algorithms, lots of common patterns that you can spot in code that help you understand, what's possible and what's not possible. So I want to cover. Hopefully, we'll touch on all of these. So the difference between best and worst case and average case, and we'll talk about these notation, this formal notation, the big O, big omega, and big theta. But I want to first look at. I'm actually going to bring up, so the way I learn these things best is to actually look at real examples in code. So I first want to look at some real examples and then kind of work backwards then to talking about some of these points here. So, but with that said, before I look at the code examples that I wanted to look at first, let me bring up these simplifying rules because I'm going to be talking about these. When I show you these code examples. We don't really need number one for this video. Number one is just kind of a transitive rule for these kinds of analysis of algorithms. So if f is in order of magnitude, if its growth rate is g of n, and if g of n is in, if its growth rate is the order of h of n, then f of n is also in that. Okay. So let me concentrate on 2, 3, and 4. So 2 says that if f, the function f, or your algorithm f, is some order as a growth rate k times g of n, then f of n is just in has a growth rate of g of n. You can effectively ignore multiplicative constants when you're talking about these asymptotic growth rates. Okay. The second one is that if f1 is some order g1 growth rate and f2 has some growth rate g2, then f1 plus f2 is just the maximum of these. So you can ignore the less expensive one. Okay, so this is important. So in practical sense, what this means is that if you have code that runs in sequence, so if you have like a really fast, a very slow growth rate, order n, and then after that you go into like a order n squared. Effectively, the slower one is not going to really impact your overall idea of how your algorithm grows with respect to the input size. So you only keep the more expensive part. All right. And then the third one, kind of in a similar way for code, if f1 has a growth rate g of 1 and f2 is g2, and if they, instead of running in sequence in code, if we have f1 times f2, then it's in order of your growth rate. You have to multiply the growth rates together. So again, this is kind of formalism here. It might be confusing, but what this is saying in a practical sense is that if you have loops, so if you have a loop where some action is repeated a number of times, then the cost of the action multiplied by the number of times, the number of times the loop happens, is going to be your growth rate. So you have to multiply those. Okay. So let's see what we mean by that here. So as usual, I'll post this example code with the video. Now I've got, if you look at this sample code, I've got a bunch of little functions that really, illustrate the basic algorithmic growth rates that you ought to be familiar with after taking an undergraduate class like this in algorithms and data structures. Okay, so we're going to look at a constant algorithm, which is known as an order 1 growth rate, an order n algorithm, or also known as a linear growth rate, and I have some others, but 2 times n squared algorithm, so growth rate of n squared, log n algorithm, so n log n, and then an example of an exponential algorithm, 2 to the n. Okay, so yeah, sorry for scrolling past these so quickly. I want to go through them one at a time here. So let's start with the basic idea of a constant growth rate. Okay, so so the first thing to understand about the analysis of algorithms is that all of these growth rates are specified in terms of n, the input size. Okay, so for all of this example code I'm using here, we're going to use our input size as 100. Okay, so think of this as our algorithms working on a list of 100 items that we have to sort, or maybe something like, or a list of 100 items that we have to search. So those are examples of what we mean by n. So and it's just traditional to use n to represent that, the input size. Okay, so let's go into the order 1 algorithm here. So a constant algorithm, basically, or you know, an O1, big O1, means that it's doing some number of operations, but it doesn't depend on the input size. Okay, so often, you know, before you actually get into your real algorithm, you have to do a lot of initialization and things like that. So those are all constant. So no matter what size your list is that you're going to sort or search or whatever, you might have to do things like initialize your indexes, like for a binary search. So create like an integer to keep track of the midpoint, and then initialize it to the value in the middle of the list, or things like that. So just think of basic initialization. So when the algorithm, so you notice here, I mean, all we're doing is initializing a variable to 5. So another quick thing I should point out here, so you should read our supplementary textbook about this, but so when you do analysis of algorithms like this, what you're analyzing, I mean, you know, you're not measuring like clock time, you know, the amount of time for various reasons, our textbook goes into. Those aren't a good measure for comparing algorithms. So, I mean, if you run your different algorithms but on different computers, faster, slower, you know, it's hard to use their actual time as measurement. So what we do for analysis of algorithms is we measure the number of operations as a function of the input size that you're dealing with. Okay, and operations is loosely defined. It can mean whatever's important for your algorithm. Okay, so for all these examples, I'm using incrementing a sum or something like that. And every time we do a basic operation, we count it here. Okay. So anyway, so for an order 1, a constant time one, though, it's not going to matter what the input size is. We're just going to do the same constant operations. So by convention, we call that big O1. So order 1, or constant time algorithm. All right. So so if we print that out, so you notice, so even though the input size was 100, if you look at the count, so afterwards, every time before I call one of these algorithms, I reset the count back to 0, and then afterwards we call this report algorithm analysis to report the actual number of operations. So in this case, we had a constant time of 1. I mean, your constant could be bigger. I mean, you could have to do 100 operations every time when you're initializing something, or 1,000, you know. So in that case, it would be O100 or O1000, but it wouldn't depend on n. Okay. So let's look at the simplest, big O of n growth rate, or this is known as linear time growth rate. Okay. So let's go ahead and step into that. So the pattern, I mean, and this is very simple, so you'll see this all the time. The pattern for a algorithm that has big O running time, or growth rate of n, runs in linear time, is that you just have a simple loop that goes from 1 to n, and you do something, you do 1 or some constant number of operations every time. So again, if we were doing something non-constant inside of this loop here, so if we were calling another function or had another loop in here, then we might not be order n anymore, big O of n. But here in this example, we're just doing a loop that goes from 1 to n, and inside of here we do order 1. So we do a constant number of operations. So if you remember back to my rule 4 where I talked about that here, that it's multiplicative. This is exactly what we're talking about here, that we have a loop that happens n times, and inside we have an O1 operation, a constant operation. So the overall growth rate of a simple algorithm like this is going to be O1 times On, which is On, which is big O of n, all right? So, and what we mean by that big O of n is that it grows linearly with the size of the input. So if I have, if my size is 100, like it is for all these examples, I'm going to do this loop 100 times, and I'm going to perform 100 operations, since I'm doing O1 operations inside the loops. If my input is size 100 million, I'm going to do this loop 100 million times, and I'm going to perform 100 million of my basic operations, whatever these operations are. All right. So so you should obviously be able to see that my count of my operations is going to be n 100 plus 1 here. So this algorithm is actually On plus O1 because we do a little bit of constant initialization before we get into the loop. We just do one operation before we do the loop, and then we do n O1 operations inside of the loop. So it's actually n plus 1. All right. So let's go ahead and step out of that. I'm going to have to continue on until there, and then we can step out so we don't go over that loop 100 times. So there. So after calling the order n algorithm, our linear time algorithm, like I said, theoretically, the upper bound on the calculation, since it's On and is 100, is 100. We did actually 101 operations because it was actually n plus 1, On plus 1, right? But again, by rule, this is something that comes out of Rule 1, Rule 3, and 2 here as well. So actually, this is directly an example of Rule 3. So in this case, the linear code that I showed you had one that was O1. So the initializations beforehand were order 1, or constant time. And then inside the loop was an order n growth rate, big O n. So we had a 1 plus n. And so in terms of overall of the growth rate, we can ignore the less expensive, the constant time one. Because again, what that means is that that the constant time one is insignificant as n gets big. Okay, so if n was a million or a billion, that initialization at the beginning becomes less and less significant. So you can ignore that in terms of how it, how much time your algorithm is going to take. All right. So that was our linear or order n, big O n algorithm here. So back to the example of the rule 2 here, talking about that you can ignore multiplicative constants. So I'll come back to this a little bit later. We'll make this clear. But if you look in this algorithm, so let's go. Let me set a breakpoint right here before the next one, and then let's step in here. So in this algorithm, we have our initializations at the top. So this is constant O1, and we have a loop that goes from 1 to n, and then we have a second loop also that goes from 1 to n. Okay, so now in this case, these are both the same order of magnitude. Okay, so we get On plus On, so we actually end up with 2n operations happening here. So as you can imagine, doing this, this is going to cause 100 operations to happen if n is 100, and then another 100 operations will happen. So we'll actually have 200 operations plus plus adding on the constant initialization at the beginning. Okay, so let me go ahead and continue on to my breakpoint out here. So what that rule 2 is saying is that again, even though actually we do 2n operations inside this loop, as n gets bigger, there's no effective difference in terms of growth rate from a 2n versus a 1n or a big O-n algorithm. Okay, so the growth rate is the same. So if I need to handle an input twice as big, in from 100 to 200, it's going to take me twice as much time in both cases. So for an O in, it would take me twice as much time. I'd have to do 200 operations. And for an O2 in, it would still take me twice as much time. So however much time I was taking to do my 2 in, my 200 operations, I would have to take twice as much time to do the 400 operations for the 2 in. Okay, but my time is only doubling in both cases. The growth is the same. Is linear in relationship to the change in the size of n. All right. So, like I said, we'll come back to that. Let's move on. So, the other important thing that I want you to get from this example code, I'm only showing the basic one. So, if nothing else, from this unit of our course, you ought to understand what we mean by a big O in or a linear algorithm, a big O n squared or a quadratic algorithm, a log n or a logarithmic time algorithm, and an n log n algorithm, and an exponential algorithm. Okay. And I should have mentioned, and I wanted to, maybe a better example, what I should have done for these is I did want to mention for each one of these what typical algorithm that you're already familiar with is an example of that type of algorithm. So if you're doing a linear search where you have a list of size of n items and you just search starting at the first one to the second one to the third one, that is a big O of n algorithm. Okay, and here I can throw in talking a little bit about the best case, the average case, and the worst case. Okay, so when we talked about linear search, we talked about its average case a little bit. So in the best case, if I have to search a list of 100 items, and I'm doing a linear search, it might be that the very first item is the item I'm searching for. So I end up just doing one operation, so big O of 1. Okay, but that's my best case. All right. But in the worst case, maybe the item isn't in the list at all. Okay, or it's the very last item in the list. So for both of those examples, you get worst case behavior. So you have to search all n items in the list. So you have to do 100 operations. So for the linear search, your operation you have to think of as the comparison. So is the item I'm searching for equal to the list at index, whatever index I'm currently looking at, right? So in the worst case, if I have 100 items, and so n is 100, I would have to do 100 comparisons to determine that the item isn't in the list, if it's a failed search, or if it happens to be the very last item. Okay, and then what we talked about though, so it's more typical if the order is, so this requires a little bit of statistics, so a little bit of a statistical background to prove this, although it's not too tough, but if the items in your list are pretty random, and if you're always looking for an item that's usually in the list, so you don't have huge numbers of searches for items that aren't in the list that are going to have a result in a failed search. So in that case, you expect to have to search on average about half of the items. So the average case is n divided by 2. And since 1/2 times n so 1/2 is just a multiplicative constant, so the growth rate in the average case for the linear search that has an average case of 1/2 n is still an O-n algorithm. So it's still a big O of n, or a linear time algorithm. All right. Okay, so let's look at n squared. So n squared is going to be our first example of, well, not exactly our first example, but our first example of a more complex application of Rule 4 here. where we have to multiply the number of actions in order to get to figure out the growth rate. Okay, so let's look at our n squared here. Step into that. So so here's the n squared algorithm. So we've done some n squared algorithms just last week. If you're in my course for this video, so the naive sorting algorithms like bubble sort and insertion sort are all big O of n squared. Okay, so they have a growth rate of n squared. So they are examples of this type of algorithm. So anytime, the pattern for an n squared is anytime you have a nested loop, so an outer loop and an inner loop, and both loops, the outer loop and the inner loop, execute n times, the number of inputs, right? So here, this is going to be exactly order n squared plus a little bit of initialization at the beginning here. But inside of this loop, the outer loop executes exactly n times, and then the inner loop also executes exactly n times. So the number of times these statements inside the inner loop actually execute is n times n, or n squared, right? Because when the outer loop is 1, we do this n, and when the outer loop is 2, we do this again n times. So it's n plus n plus n. Added up n times, or n squared, right? So yeah, I mean that's going to be, we're going to end up doing n squared operation. So if input size is 100, we don't do linear like 2n, 200. We're doing n squared. So we're going to be doing 10,000 operations, 10,000 times in this inner loop for an input size of 100. All right. I must have gone a little bit too far. I skipped past something. Sorry about that. So if you look at the n squared one, so yeah, in terms of the number of actual operation counts, it is 10,000 plus the constant initialization at the top, which in this case we only are doing one initialization, so it's 10,000 ones. But we have an order, so our big O is n squared. The expected is 10,000 operations. Okay. So I skipped over this, so I'll just scroll back up to that one. So another example, another common pattern here. So the bubble sorts. Actually, I think all three of the algorithms that we looked at for sorting, not naive sorting algorithms, were more like this pattern. Okay, so the outer loop would execute exactly n times. So remember, for bubble sort, that we always execute the outer loop n times, but the inner loop we would only go up from the beginning up to the end of the list that had been sorted so far. So here the inner loop goes from 1 up to whatever outer is in this case. So bubble sort, it started going from 1 to n, but as the outer loop executed, the inner loop would go less and less. Here the inner loop, the first time the inner loop executes, it only executes 1 time. Then when outer iteration is 2, it executes 2 times, and so on. So the actual number of times that this statement here inside of the inner loop executes is 1 plus 2 plus 3. So it's the sum of the series, 1 plus 2 plus 3 plus ... plus n. Okay, and the sum of that series is n times n plus 1 divided by 2, right? So yeah, n times n plus 1 divided by 2. That's what the sum of that series is. But again, this is still a big O of n squared algorithm. It's just the top is n squared plus n, and so it's 1/2 times n squared plus 1/2 times n. Okay. So again, and then by rule 3, you can ignore the 1/2 times n. That's a slower growth rate than the n squared. And by the rule 2, you can ignore the multiplicative constant of 1/2. So even though this is 1/2 times n squared times n, the big O, the growth rate in terms of how it's going to grow with a change in your input size is n squared still. All right. So, so yeah, if you go back to our output for that one that I kind of skipped over, but yeah, you see the expected. I should have left this as 10,000. So it's big O of n squared. So it is 10,000. But the actual number of operations is n times n plus 1 divided by 2 plus that one constant one, the initialization at the beginning. So it's 5,050 plus another one with the actual number of operations you do for that kind of pattern. Okay, but that's still a big O of n squared algorithm in that case. All right. Okay, so let's go back. So I kind of I looked at linear order n. Order n grows slower than n squared. So n squared is a faster growing order time growth than linear, than order n. Okay, so here's one that's actually faster than linear. And we've seen an example of this, a logarithmic time algorithm, so logarithmic time complexity. All right. So anytime you take your problem size of size n, and instead of having to search through every item one by one, like in linear, if instead you can do something like eliminate half of the items from consideration at every step, then you're going to have a logarithmic algorithm, so log log 2 algorithm in that case. Okay, so the binary search algorithm that we looked at is the quintessential. It's the prime example of a log 2 order, or an order log 2 algorithm. So an order log 2, a big O log 2 logarithmic time algorithm, right? Because for binary search, every time you look at the midpoint of the unsearched portion of the list, and from that you can eliminate, so the item you're searching for is either less or bigger than that midpoint item. So if it's bigger, you can ignore all the smaller items than the midpoint and search again on the items that are bigger than that, and vice versa, right? So so let's just step in there. Let's look at an example of what I did there. Oh, sorry, I wanted to step in that. Well, so I'll go up here. So here's the logarithmic algorithm, so log n algorithm. So the pattern is it's a loop, so you do have to be careful. I mean, not every loop is linear, so not every loop results in an order n. So in this case, the loop goes from 1 to n, but every time we're multiplying, instead of adding 1 to our index variable, iter in this case, we're multiplying it by 2. So the first time it's 1, and then 2, then 4, 8, 16, 32, 64. So this is going to only go, this inside this loop is only going to execute log base 2 of n times, right? So the log base 2 of 100, so that's 2 raised to what power is 100? So 2 raised to the 8 is 64. Or 2 raised to the 6 is 64. So it's around 6 or 7 basically, right? So this loop will only execute 6 or 7 times, right? It'll be the maximum of that. So I think if I did my if I did my binary right, it is 7 times, right? But that's a much lower number of times this loop happened. It's a much slower growth rate than order n. So if instead of being 100, n was 1,000,000, that's 10 to the 6. If this was log base 10, then we'd only have to do this loop 6 times. So log base 2, I think it's 20, 2 to the 20 approximately. So instead of doing 1,000,000 times for linear, if we're doing this log 2, so n is 1,000,000, we'd only execute like 6 times, right? So this grows much slower in terms of your time complexity than even linear time. This is not the only way you can get this pattern. So you can commonly get this pattern from recursive algorithms. So recursive binary search would do the same thing. or the binary search algorithm that we looked at. So so for the binary search, you would be looping, but you would loop just when when the number of items in the remaining portion of the list reached 1. But every time through the loop, you'd be selecting a midpoint and then changing your left and right to eliminate half of the items in the list from the search. So every time you do the loop, only half of the items remain. So that's another way you can get logarithmic log 2 growth rates in your algorithm. So yeah, let's just print that out. So for the login, yeah, so I was right. It happened 7 times plus the one constant at the beginning was still in count. So it was 7 plus 1 are the actual number of times. The theoretically the 2 raised to the 6.6 gets you 100, right? So log base 2 of 100 is 6.6. So usually you have to do the max of this. So a loop like I showed you is going to run 7 times. So you have to take the ceiling of this to see how many times the loop will actually run if you need to count up actual number of iterations. All right, and then so then another one besides logarithmic time is in login time. Okay, so in login time. This week we our programming assignment, we're going to be looking at a better sorting algorithm than like the bubble sort. So the best sorting algorithms work in login time. Now in login time is a better growth rate, so it's slower than in squared. Okay. So because log n grows much slower than n, log n times n is slower than n times n, right? So we consider in log n to be quite a bit of a big improvement over n squared. So again, for 1,000,000 items, an n squared algorithm, sorting algorithm is going to have to do 1,000,000 squared, or 10 to the 12. So 1,000,000, 1,000,000, right? But an in log n algorithm, remember the log n is about 20 for 1,000,000. So in log n only does 20 million. So it's still pretty close to linear time. It's like multiplying just by a constant factor of 20, and the log grows really slowly. So in log n algorithms are good in terms of their performance, right? They're almost as good as linear as big O of n, right? So let's step in there. Let me make sure I step in there this time. So the common pattern for in log n is you have an outer loop that does the same thing we did for the logarithmic, but it has an inner loop that performs n times. Okay. Or vice versa. So the good sorting algorithms that we're going to look at this week, like merge sort or quick sort, they have an outer loop that happens in linear time, that happens n times, but the inner loop happens only log n times, right? So anyway, by that multiplicative rule 4, the outer loop is n, the inner loop is log n. So these two loops combined, when we multiply them together, is big O of n times log n. So it's an O in log n plus our initializations plus the order 1 here, right? So we expect this for size 100 to be the 6 times 100. So about 600 times for this operation to occur. Actually, the inner loop is going to happen 7 times again, the ceiling of that. So this will happen 700 times plus 1, right? So let's show the output of that. So yeah, we get 701, expected. The O in log n would be 664, right? Because log 2 of n is 6.6 times n is 100. All right, and then as a final one, let's look at exponential growth. So exponential growth happens anytime most brute force algorithms tend to look like exponentially growing. Tend to be exponentially growing algorithms, okay? So I'll give an example of that here real quickly. So this algorithm, so something like 2 to the n. So notice here, instead of like n squared where the exponent is a constant too, here the exponent grows as our input size grows, okay? So this grows much faster than n cubed or n squared algorithms, okay? Another algorithm that's considered to be exponential is n factorial. N factorial is even worse than exponential, okay? So it's even worse than exponential if you have a factorial growth algorithm. So let's just step in here. So I had some examples. So if you don't know what I mean by brute force, here's one example. So a naive way to implement the 8 queens problem, if you're familiar with this, try to put 8 queens on a board so that none of them are attacking each other, is to use this data structure here, and to realize that only, every column has to have only one queen on it, okay? So then you represent this as the row that you put the queen in each column in. So this represents that the queen in column 1 was in row 1, the queen in column 2 was in row 2, the queen in column 3 was placed on row 4, and so on, okay? So a naive algorithm is just to start by generating all possible queen placements. So this represents all queens are in row 1, and then you test that, whether that's a board position where none of the queens are attacking each other. Now if you do that, of course you get, you have to do 8 raised to the power of 8. So it's actually n to the power of n. It's not 2 to the n, it's n to the power of n. But that's again an example of an exponential algorithm, because you're going to have 8 raised to the power of 8. You're going to have to go through 8 raised to the power of 8 possible board positions to find all of the valid ones where the 8 queens are not attacking each other, right? Which is what the problem here is about, right? So another common one is if you implement recursion, where you solve the big problem by breaking it into 2 smaller n-1 size problems and then recursively solve those. So a naive implementation of the Towers of Hanoi that uses recursion does that. That's also 2 to the n. That's an actual 2 to the n instead of n raised to the n. But that's also another common pattern where you get exponential growth rate. So recursion, where you're solving 2 n-1 subproblems recursively. So I showed that example here. So in this case, we say that we're doing a recursive algorithm. If the base case is 0, we just return 1. Otherwise, we call ourselves recursively twice on a problem of size n-1, so it's a size smaller. So 2 to the 100 is a number with 31 digits. So if you actually left n as 100 here, your computer would be calculating for a long time. In fact, actually, probably it would blow your stack. You probably would run out of memory before you actually reach the end of your calculation, even for an input size of just 100. Right? So but anyway, if you do like 15 instead, if we can handle it. So, oh yeah, I did step over that. So even for just 2 to the 15, so even for just an input size of 15, we're doing over 30,000. So we're doing even much more than our n squared algorithm for an input size that's 1/10, or less than 1/5 of the input size for the n squared there. So. All right, so kind of just summarize this before I go on to the next point here. So, I mean, it is important. I think this is very useful. This is a skill that will help you a lot if you're going to get into software or computing systems, is to understand these basic algorithms. So what the difference is between logarithmic time versus linear, big O n, versus n log n, versus a quadratic time algorithm n squared, or a cubic time algorithm n cubed, versus an exponential algorithm like to the n, right? So in practice, so in the theory of computer science, the theory of algorithm analysis, they look at a lot more complex cases like that. But in practice, I mean, that if you know those and kind of understand the difference between those, those will be what you'll almost always run into in real implemented systems. Some example of those basic ones that I just talked about. So, all right. So let's look at a little bit more detail. Let's compare the performance of those basic algorithms that we looked at. So this is pretty similar to one of the figure from the supplement or textbook that I'm having my class go through on this class, except for I simplified it pretty much, so I'm only using those basic ones that I talked about. So we have a logarithmic algorithm, which I didn't label, so that's the kind of the blue one here, and then a linear in, then in log n, in squared, in cubed, 2n, and in factorial here. All right, so the first thing is, our input size only goes up to 15 here. So this is going to be the number of operations for each of these for a size size input 15. For n cubed and our exponential and the factorial, it's so big that I just cut it off. So these take many more operations than 500, and I'll show that in a second here. But these grow much faster, although it's a little, so I'll show it in a second here. So n cubed and n squared, even though they look like really big differences here, these things, most people that are designing algorithms don't consider an n cubed really that bad. I mean, it's still practical to do n cubed algorithms even on really large inputs, like for matrix factorization or things, or matrix multiplication. But two exponential algorithms or factorial algorithms are not practical. You can only do toy problems, So, for example, the traveling sales. Another example of a exponential algorithm is, you might have heard of the traveling salesman's problem. So there are algorithms that can solve that, not to find the best possible path. So the one that has the absolute minimum time, and those work better. Those work in like a in squared or n squared log n time, I think. But if you have to get the absolutely best path, the one that has the minimum for the traveling salesman problem, it's known to be, it's believed to be a exponential complexity. You can't do any better than kind of a brute force search on that. So. Okay, so anyway, so the book also makes a similar point, but using a different one. So what you should understand about the growth rate of these and why we consider n log n different from n squared. So knowing that something has an upper bound of n squared versus has an upper bound of n log n versus something has an upper bound of n cubed, no matter what the constants are or additional expressions, is very useful. Okay, so like this. So this is an example. I've only just used constants here, but I could have done the same thing. So if you compare like an n log n algorithm, but let's say we multiply it by a constant factor. I just did it 3 in this case. Okay, so I mean it's worse than n squared in terms of the number of operations up to a point. Up to about an input size of 10, but at that point it gets better. I mean, it's better. It's a faster performer than n squared. Okay, and the point with those rules, those simplifying rules that we gave. So if I had an algorithm that was 100 n log n plus 1 million n plus 10 million. Okay, so I have a big multiplier, 100 n. Plus I have some other slower growing terms. So what did I say? 1 million plus 1 million n plus a big initialization, 100 million. So even that, its growth rate is still n log n. So if you make your n big enough, so even that, no matter how big you make this constant in front of n log n, once n gets large enough, this will go below n squared. So it grows slower than n squared, and so no matter how big your multiplicative constant is or other terms are that are slower growth rates, eventually it will be faster than an n squared algorithm. All right. So that's why these big O's, these time complexities are important. Right. So if I know it's an n log n versus n squared, that tells me something important about my algorithms. Same for if you look at n squared versus n cubed. Okay, so I'm making the same point, but if I have an n squared algorithm, so even if I have like an n cubed algorithm that's only 1/10, so my multiplicative constant is making it slower by 1/10 than a standard n cubed. So n squared does worse than n cubed for a while, but at some point that n cubed is going to be worse than my n squared. Okay, it doesn't matter how small I make this, 1/1000th, 1/1,000,000th. As long as it's just a constant greater than 0. At some point, that n cubed algorithm, once n is big enough, is going to be slower than an n squared algorithm. All right, so that's an important thing to understand. So if you didn't quite follow me on this, you make certain you kind of go back and read our textbook and think about that. So back to these exponential algorithms. So if I had actually, I'm still cutting off here. I'm cutting off higher, so instead of 500, I'm cutting off at 50,000 for the number of operations. So even that is not big enough for n factorial. It's still, when we have input size of 15, it's still much bigger than even 50,000. Although you can now see the 2n and the n cubed. So this does give a better feeling for n cubed and n squared and n to the fourth. They're still, these are if you ever heard of the p versus np question in theoretical computer science, this is what it's talking about. Polynomial time complexity algorithms are things like that have that are polynomials that have a constant for the exponent. So something like order has a time complexity of n to the fifth plus 3n cubed minus 4n squared. So that's a polynomial. That's known as a polynomial time complexity. Those are considered always much better than anything that's exponential. So NP stands for non-polynomial in the P versus NP question. So things that are non-polynomial are exponential, like n factorial or 2 to the n, and they are usually going to be impractical for anything but like toy problems with only 100 inputs or 10 input, depending on what you're doing. All right. So another thing that's related to what I was just talking about, again, related to this idea of growth rates. So this figure, again, is also directly from our supplementary textbook, except for I added a little bit for the sake of discussion here. So if we want to compare an order n to an order n log n to n squared, n cubed, or exponential algorithms, this is the correct way to think about it. So in this example, we were talking about having a computer that increased 10 times in speed, okay? So if beforehand, if I had an algorithm that was linear but 10n, and if beforehand my computer was fast enough to process an input of 1,000 items and whatever my time limit was, like let's say a minute or a second or whatever. So for my 10n algorithm, 1,000, if my computer increases in speed by 1 order of magnitude, I will be able to process 10,000, so 10 times that, okay? So the ratio, for a linear algorithm, the ratio of what I could do before for whatever my algorithm was to what I can do now when I increase by some factor, like a factor of 10, is 10. And it doesn't matter what your multiplicative constant. So this is one reason why for these growth rates, the multiplicative constant doesn't matter as far as comparing the growth rates of these algorithms. So if I have a 20n algorithm, of course, I mean, it's worse than 10n. So in that same amount of time on my original computer, I could only maybe process 500 versus 1,000, right? But this is linear in time. So if my computer increases in speed by 10 times, it will also be able to go from a problem size of 500 to 5,000 in the same amount of time. So again, the problem size I can handle also increased again by 10, by a factor of 10, the same as the speed of my computer increased. Okay, and that's because it's linear, right? So there's a linear relationship. So the all these others are nonlinear. So everything in log n logarithmic is below linear, but I didn't show one of those. In log n, let me go to n squared first, and then we'll come back n squared and n cubed, and then we'll come back to n log n. So n squared, on my original computer, and this is assuming kind of the same problem. But if my algorithm to solve the same problem was it was a 2n squared algorithm, on my original computer, I would have been able to process an input size of 70 in some time limit, right? So now if I have a computer that's 10 times faster, n squared would allow me to do 223 if you work out these, right? Because it's going to be the square root of 10 times n, right? But that's not so for an increase in the speed of my computer by 10 times, I was only able to handle problems that are 3 times bigger in the same amount of time. Okay, so n squared does a lot worse than a linear, an order n algorithm, right? So increasing my computer speed by an order of magnitude only allows me to, by 10 only allows me to increase my problem size I can handle by 3 every time. So if I get a 10 times faster computer again, I'm only going to be able to handle a problem size of about 600 in the same amount of time, 660, 670. Okay, that's what they're saying. N cubed, the same thing. So, but it's going to be worse. So, if my speed of my computer increased by 10, it's going to be the cube root of 10 is the size of my new problem that I can handle in the same amount of time. So I'll only be able to handle problems that are a little bit over twice as big as what I could before if I increase by an order of magnitude the speed of 10. Okay. And logarithmic is going to be somewhere between n and n squared is what this means here. So if my constant was really, really big, I could push this to be pretty close to linear. But if my constant is non-existent, if it's really, really big, I could push this to be close to n squared. So square root of 10. And if it's like 1/1000th or something like that, it's going to approach a linear. It's going to be almost linear, even for really, really big problems of size n. So, but yeah, on average, it's about 7.3. So, and exponential algorithms, forget about it. So, increasing my speed of my computer by 10 only increases my problem size by 3 items. I can only do a problem of size 3 in the same amount of time. And if you work that out, I mean, even if you so if I want to double the size of my problem, so if I want to go from a problem size of 13 to 26, I don't need a computer that's 10 times faster or 100 times faster. I need a computer that's 10 to the 8 times faster, approximately. 100 million, if you work that out, because log so that's the basic idea. So exponential, again, the point of that is that it just they're impractical, so you're not going to be able to solve real problems with an exponential algorithm, even if you can get an unreasonably fast supercomputer, right? You're going to have to do something about the algorithm, get a better algorithm. So that's why non-polynomial time algorithms are of a lot of interest. Is there some way to find a better algorithm for those that will run in polynomial time? All right, so as a last thing, kind of common misunderstandings. So this is a big one. I pretty much skipped over this. The supplemental reading I gave you did talk about big O versus big omega versus big theta. Okay, the thing about this is that most of that is really only when you get into theoretical computer science. So if you take a graduate course in algorithm analysis where you need to work on the theory of like the P versus NP problem or something like that. In almost all practical situations that I've seen, though, it's easy to recognize the true growth rate. So if you have complete knowledge of the code, so if you have the actual code, you can analyze it and tell exactly what its growth rate is. And in that case, the upper and lower bounds, so your big O and your omega, are going to be the same. So when we know that the upper and lower bounds are the same for an algorithm, we can say that it has a big theta for its growth rate. So it would have been more correct when I talked about this all in this video previously if I'd been calling that big theta of n instead of big O of n. But you will find that computer scientists and working software engineers in the real world usually use big O. But they usually mean that because they're talking about known algorithms, like a quicksort algorithm or something. So it's known to have both an upper and a lower bound of n log n. So it's actually a big theta growth rate of n log n. So it won't do worse than n log n, but it won't do better than n log n. So don't confuse the upper and lower bounds with the best, worst, and average case performance. So big O and big theta, that's talking about upper bounds and lower bounds. A big theta means when both the upper and lower bound are known to be the same for an algorithm. Now we've talked about best, worst, and average case last week before. So and I already talked about it in this video. So I mean even though worst case doesn't happen when you have a bigger input. Okay, so you're not going to get your worst performance when you have n that's billions. Your input size is billions. Okay, that's confusing worst case with upper bound. Okay, you're going to have your worst case depending on the type of the input. So again, back to the linear search. You're going to have your worst case if you're searching for an item that's not present. In that case, you have to search all the items, no matter what number of items you have in your list. Okay, that's an example of worst case. And the analysis of worst case for that is that worst case is ON, whereas the analysis for average case, it has an upper bound of ON divided by 2, or 1/2 ON, because on average you only have to search half of the items. But the best case has O1. So the best case is that the item always happens to be the first item that you're going to search for. You just do one search, so you're done in constant time, O1. So you can. The other way of saying that is that you always have separate analysis for the best, worst, and average case. Okay, so I can have a big O analysis for the worst case. A big omega analysis on my upper and lower bounds for the worst case, and if those are the same, I'll be able to state my big theta for the worst case. Same for average and best case. Okay? And usually best case is not all that interesting. So usually you need to be conservative when you're trying to do an analysis of your algorithm. So most useful is usually the most informative is usually the average case because that's going to what's going to normally be happening, assuming that you know what the average case is appropriately, right? But if you need to be conservative, then you want to find out what input is going to cause your algorithm to perform at the worst, right? So for example, the quicksort algorithm that we're going to be working on for the assignment for this class. Hopefully I'm remembering this right. But I mean, it has an average case of n log n, and its best case is n log n. It won't really do better. But its worst case is if you give